Abby, you might be able to pick this up without watching the video lesson. We'll see. So here's what we said. We're all on this little picture here. We had Manuel the painter, and we argued, and I think it was Cole that I picked on, that the total force down was 1,200 newtons. And I said something like this: is he sinking into the ground like quicksand? And you said no. Is he flying through like Superman? And you said no. What I really mean is he accelerating? And you said no. So the forces must be, I'm looking for the letter B. So if there's 1,200 newtons down, there has to be 1,200 newtons up. And because he's dead center, the two supports would split at 600 and 600. Second picture. What's the total force down? Still 1,200. Is he sinking into the ground like quicksand? Is he flying at you like Superman? No, you say. Then the total force down has to equal the total force up. Forces must be, I'm looking for a word that begins with the letter B, balanced. Now, he's moved over. He's off center. So one support is pushing up with 850 newtons. What must the other support be pushing up with? It's got to be 350. Has to be. And I know that because of Newton's first law. You can even use this, Matt, in bridge design. Matt, I have a 12-ton truck and a 20-ton bridge. What's the total force, Matt, pointing down? Do the math in your head. 32 tons. Is the bridge sinking into the ground like quicksand? I hope not. Is it flying into the air like Superman? I hope not. So forces must be, I'm looking for a word that begins with the letter B. So what was the total force down? 32. I got 13 tons on this support. Folks, do the math in your head. How many tons must this support be pushing up with? 19, I think. Yes? And so you can see where this would be used in bridge design as well. Much more complicated than the simple situation with one truck, but you can extrapolate from there. In terms of Newton's first law, the law of inertia, how does a car headrest help to guard against whiplash when you get rear-ended?
It stops your head from flinging back.
I gotta be fussy. It doesn't stop your head from flinging back. How fast is your head traveling when you're at rest? 0. Newton's first law says your head wants to stay at rest. Your body gets flung forwards. Your head doesn't get flung back. Your body gets flung forwards, and your head wants to stay at rest. What the headrest does is it applies a force on your head to keep your head with your body. You see, I'm being fussy, but I'm telling you, your head never got flung back. That's impossible. It stayed where it was. Your body got flung forward. I think I told you the car accident story last day about my ashtray appeared to me to go shooting over my shoulder. No, it didn't. It stayed where it was. My car and my head got thrown forwards. So I'm being fussy, but you understand why I'm being fussy? You got the difference? Yeah. Okay, so headrest applies a force to keep head with body. Anybody here been rear-ended before in a car accident? Okay. Most of you are getting your license in the next couple of years, and in the next few years, most of you will be getting your first car. Please, and I'm being serious now, when you get your car, take 10 seconds to adjust the headrest. It's such an easy prevention. When I got rear-ended, I had not adjusted my headrest properly. And so the next day, I got whiplash. The next day, I felt pretty good. I thought, this isn't so bad. It's 2 days later, you suddenly find you have thousands of microscopic muscles in your neck and in your shoulders. Have you ever had someone dig their thumb into that nerve point right there? It felt like that for about a day and a half, that permanently someone was just digging their thumbs into that point. And it's preventable. Set your headrest up properly. You'll still be a little sore. Not as sore as I was. It's not a pleasant experience. Newton's first law, objects that, you know what? Newton's first law, are you accelerating? The forces aren't balanced. Oh, you're not accelerating? The forces must be balanced. Newton's second law is the equation. It is on your formula sheet, but this is one that's worth memorizing because you're going to use it so much. It says this: force, F, equals mass, M, times acceleration, A. Where the mass is in kilograms and the acceleration is in good old meters per second squared. You'll notice, William, that force has a vector symbol. and A has the vector symbol. In other words, do you want to know which way the net force is? Which way you're accelerating? Same direction. Or if you know the direction of the unbalanced force, that's the direction that you will be accelerating. They get their directions from each other. What was the units for force? Do you remember? Newtons. So here's what that means. It means that 1 Newton is actually the same as 1 kilogram meter per second squared, because that's MA. And that's what we used to write for a long time. We would write forces measured in kilogram meters per second squared. But you'll find often when we have a lengthy combination of units, we'll name them after a scientist. For example, you may have heard of volts. Volts are actually a joule per coulomb. And what's a joule? A joule is actually a Newton meter. So a joule is actually a kilogram meters per second squared meter. And a volt is really a kilogram meters per second squared meter per coulomb. A watt is actually a joule per second. All the units, we start to name them after people. And you'll find later on this year, I'll let you in on one long unit that hasn't been renamed, but it might get renamed in your lifetime. They're talking about calling this particular future unit an Einstein, because he doesn't have one named after him, and he probably should. Example 4. Malcolm has a mass of 64 kilograms. What is the magnitude of the gravitational force acting on him? Haley, what's this question you wanted me to find? The magnitude of what? Gravitational what? Gravitational what? Force? Gravitational what? Force? Gravitational what? Force? Stop. Don't write this down. Here's what my brain is going to start to think. F equals ma. Don't write that down. By the way, F equals what? F equals what? F equals what? I'm going to keep going until I see August's lips move as well. F equals what? I didn't see Matt's lips move. Everybody, F equals what? Ma. Okay, F equals mass times acceleration. The reason I'm doing that, that's the one you're going to use like crazy, and hopefully you've just memorized it. You don't have to look it up. Okay. What's the acceleration due to gravity? You know this. I said magnitude, so ditch the negative, just plain old. Here's what we're going. I'm going to give you your first official force. I'm going to use the letter lowercase g for gravity, and I'm going to use F with a subscripted g for the force of gravity. Write that down. All of you probably have a mass between 50 and 75 kilograms. All of you right now are under the force of gravity. How do I know? Because you're not floating. Okay, so for Malcolm, he's going to be 65 times 9.8. I can do that in my head. It's going to be 650, take away 13. Is it 637? Double check me. Okay. Malcolm feels a force of gravity at all times of 637. What are the units for force? You told me. What are the units for force? Newtons. We have a special name for the force of gravity. The special name for the force of gravity is weight. Mass is not the same as weight. Mass is measured in kilograms. Weight is measured in... Weight is your mass times whatever gravity is on what planet that you're on. So your mass doesn't change on the moon. Your weight does, because on the moon it's not 9.8. Your weight would change on Mars. Your mass wouldn't change. You okay with that? Matt, stand on your desk, please. Dead serious. Stand up, stand on your lab table. I may be fulfilling some childhood fantasy. I don't know. Okay. Take a look at Matt. I wrote in part B, Malcolm. Matt's going to be our Malcolm analog. So Matt, Malcolm, same thing. Matt, Malcolm, stands on a table. What is the magnitude of the upward support force that the table exerts on Malcolm? And I wrote, hint, represent Malcolm with a dot and draw the forces. Stay standing. You'll write this down in a second, but we're going to use you as our analog. You can glower down at us from on high. We're going to represent Matt with a dot. Put a little dot right there. What are the forces acting on Matt right now? What's the obvious one that we know is acting on him right now that we've just finished talking about? Begins with letter G. Draw an arrow pointing down, and let's label it FG, force of gravity. That can't be it, because look at Matt right now. Is he sinking through the table like quicksand? No. Is he flying through the ceiling like Superman? No. In other words, is he accelerating? That means the forces on him must be, I'm looking for word, letter B. There has to be a force pointing up, and I can tell you exactly how big it is. The arrow is going to be the same length as the arrow that I drew pointing down. I'll give that force a special name. I'm going to call it F sup for support. You see why it has to be there? It has to be there. The table has to be pushing up on you. And this is a bit strange, Matt, because people aren't used to thinking that inanimate objects can apply a force. Absolutely they can. You don't have to be living to apply a force. The table must be applying a force. Otherwise, you would be sinking into the ground like quicksand, because that's what Newton's first says. Not only that, I can tell you exactly in newtons how big the support force must be for Malcolm Matt. How big must the support force be if that was Malcolm standing there exactly in newtons? Darn right, it's got to be exactly 637 newtons. If it was 636 newtons, Matt would be sinking into the ground like quicksand through the table. If it was 638 newtons, you would be accelerating up. Are you? Then it must be balanced. This is the power of Newton's first law. It can help you determine the magnitude of missing forces. Thanks, you can sit down now, kiddo. How do we know that this force exists? What law did we use? Which one? There's going to be 3 of them. Newton's what? Now, listen up. I am going to ask you to know all 3 of Newton's laws. You don't need to memorize which one is which. You can if you want to. The law that we used is Newton's first. And so I'm going to write as my explanation Newton's first law. If you can't remember whether it's Newton's first or second or third, you could actually just explain the law. Matt isn't accelerating, so forces must be balanced, and I will give you full marks there. So you don't need to necessarily memorize which one is which, but my kids that have a lazy streak and have a bit of an inner nerd, they'll often memorize which law goes with which, so instead of explaining it, they can just say the law, name, drop the mic, and walk off. Newton's first law: if you're not accelerating, forces must be balanced. If you are accelerating, they can't be balanced. Newton's second law, everybody, are you ready? F equals what? F equals what? F equals what? By the way, this diagram here is going to be the DFIC of this unit. Remember a couple units ago, it was write down what they found, list what they gave you. That was your go-to starting point. This tool, this diagram, is the single best tool I'm going to give you in forces. If you talk to my Physics 12 students, they've probably done a few hundred of these. We call a diagram like this, where you represent the mass with a dot, and you list the forces with arrows. We call it a free body diagram. Although, because you know I tend to I'll often abbreviate it as FBD. So you may be doing the homework, and it'll say something like, hint, draw an FBD. Let me draw a free body diagram. Okay. Newton's second law, F equals ma, that already explains some stuff. Example 5, turn the page. The space shuttle, I missed the space shuttle. I grew up with it, and so it's my Starship Enterprise. The space shuttle has a mass of 2.03 times 10 to the 6 kilograms. That's accurate. I lifted these numbers from the NASA website. Each engine, the 2 big booster engines, each engine can exert a thrust of force of 12.5 The capital N is newtons. What does a capital M as a metric prefix mean? Which one is that? Micro? No. Mega. Oh, okay. So each engine can exert a force of 12.5 meganewtons. Dan, what's A asking me to find? Okay. Don't write this down. This is what my brain would think. The first thing my brain would say, oh, good gosh, acceleration. I might think, don't write this down, well, VF minus VI over T. Did they give me a VI or a VF or a T? No. I might think VF squared minus VI squared all over T. Did they give me any of that? You're going to find, Chelsea, that acceleration is such an important concept. You'll have many, many, many ways to find it. So instead, I'm going to say they gave me a mass, they gave me a force. Is there an equation that has an F and an M and an A in it? F equals? Let's write that down. And hopefully now you're starting to see why I pummeled you so much before Christmas with this formula manipulation thing. Chelsea, how would I get the A, since that's what they want me to find, by itself? How will I move the M over? Divide what? Use nouns and not pronouns. Did you say F divided by, divide the M over, yes, okay. Do I need to memorize that equation or can you derive it safely now? Yes. So you want me to find the acceleration? Okay. It's going to be F divided by M. What's the force? How many engines are there? How many of those big boosters are there? So I'm going to have to multiply by 2. That's why I said note there are 2 engines. And then the force on one engine is 12.5. Mega is 10 to what? It's on your formula sheet, but I'm gambling. Maybe someone remembers. If not, if you happen, yeah.
10 to the 6th.
It's 10 to the 6th. So I'm going to go times 10 to the 6th. There's the force divided by, the question says the mass is 2.03 times 10 to the 6th. Everybody get your calculators out. We're going to be doing some fairly complicated calculator stuff, so I want to strongly advise you for this unit to always practice following along on your calculator. Try typing this in. 2. Do I need brackets? This is where you want to start to play around with your calculator. I know, Oscar, on my calculator, if everything on top is multiplying, I can do without the brackets. The bottom, usually if there's more than one thing, I need brackets, although I have a feeling with my scientific notation button, I probably would have been okay without, but better safe than sorry. And see if you get, I got 12.3, double check me, see if you get that. Now, if you didn't get that, later on, you want to snag me and we'll walk through how your calculator works. Anybody else? Show me a 12.3 nod. Nod. Yeah? Okay. Units, it's acceleration.
Meters per second squared.
Is that a lot? You know what? How many G's is that? How do I convert meters per second squared to G's? It was something with a 9 point. Oh, divide by 9. Could you divide that by 9.8? How many G's are the astronauts pulling? How many?
1 point.
Did you say 1 point something? Mr. Dueck, I thought the astronauts were pulling like 6 or 7 G's. That's what I've heard. We just run the numbers and we got like 1 point something. Has NASA been lying to us all this time? B. Why does the acceleration change as the engines burn? And I'll give you a hint. The acceleration increases. Why? So far, one class couldn't figure it out. One class could figure it out. So you're my third class. I'll see if we got somebody who can have that aha moment. Yeah. Force does not increase. The engines are at maximum thrust and it stays the same, but you're on the right track. as you burn fuel, what happens to the overall mass of the space shuttle as the fuel burns up? Okay, did you hear Cole? Oh, you get lighter. Now look. Here's our equation for acceleration. If you start to divide by a smaller and smaller and smaller number, what happens to this answer? Bigger, smaller, or stays the same? When you divide by it, when mass gets smaller, A gets bigger. You know when the astronauts are pulling the most G's? Right before they shut off their engine and get into orbit. And we don't see that on TV. How many of you have seen a rocket launch like the space shuttle on TV before? It looks very slow and majestic. I don't know if you've ever thought, I thought they were pulling a lot of G's. They are later, not right away. So, A equals F over M. Same equation, Newton's second law rewritten. As M gets smaller, my abbreviation for gets smaller or decreases is an arrow pointing down. A does what? Increases. My abbreviation for increases is an arrow pointing up. Hey, how does Newton's second law explain why a sprinter might want to wear lightweight shoes? Pardon me? What do you mean so it doesn't hold them down? Can you use physics words, please? I think you're on the right track, but I want some physics words. I'll give you a hint. Why would that explain why a sprinter, if you're in the Olympics, would want to wear lightweight shoes?
Your mass is lighter.
And so if your mass is lighter, what gets bigger?
Acceleration.
So let's suppose you're a professional sprinter, okay? And you've lifted weights so that your legs are as strong as they can be. So you've maximized the force. You muck around with the mass still. So here's the next question. Same answer as before. As M decreases, A increases. So why don't sprinters run barefoot? Because wouldn't that be the logical conclusion? Why don't they run barefoot? You've learned enough physics. Think about it. What would be the issue if you ran barefoot? Oscar, give me a guess. Make a hypothesis.
Oh. Well, I was thinking just because they do have grip.
Yeah. There's a fancy word for grip. It's the force of friction. We're going to use that word. We're going to do a whole lesson on friction in a few days. So you wouldn't have enough friction. So that's the trade-off. Here is Mr. Dueck's prediction. See if we see this within 20 years. Okay? I'm a little amazed no one has invented a liquid rubber that you paint on to the athlete's feet, just to the bottom, and then the athlete steps on a tread mold to put some tread on there. And for one race, they wear this sticker on the bottom of their feet, and at the end of the race, they just pull it off like a sticker. That, to me, seems to be the ultimate in that's the smallest mass you could get, and I'm a little shocked that no one has designed or developed something like that.
How would that not rip off as a running?
You designed something where it was glued on a little bit. And you, as long as it would last for a 100-meter race, you'd probably build it so it would maybe last for a 400-meter race. And so you'd know you had a safety margin for 100 meters, and you'd peel it off. And that would give you an adjustable tread. Depending on the track, you would use a different mold. I'm a little amazed no one's coming up with that. If any of you become chemistry materials scientists and you decide to try and invent that and make some money, just thank me in your speech. But that to me would be the logical step, because you'd have only mass on the bottom. You'd save the shoelace mass, you'd save the material mass. And when you watch the Olympics, you guys, especially for the 100-meter, you've seen the difference between first and fifth is like 5 1,000ths of a second. We're talking just a tiny bit of mass, William. It's got to make a difference. Sorry, what was that? Did they do that? He did spray-on shoes, but those were all the way over the top. I'm just thinking something on the soles. That would take care of the friction issue and maximize, or I guess minimize, the mass. Just a thought. Newton's third. So Newton's first law, objects are going to keep going in a straight line at a steady speed. If you're accelerating, there's an unbalanced force. If you're not accelerating, their forces are balanced. Newton's second law, everybody, are you ready? F equals what? Newton's third law is often phrased, for every action, there is an equal and opposite reaction. What? It's Mr. Dueck's version. Forces come in pairs. Forces come in what? Forces come in what? Here's what that means. That means you have to have two objects for a force to exist. If you have an object floating in outer space all alone by itself, it cannot experience a force. A force has to be an interaction between two objects because forces come in. If you want me to write this mathematically, Matt, it would look like this. The force of object A on object B is the same as the force of object B on object A, except they're in the opposite direction because they're pushing on each other. What would be an easy way to show that it's in the opposite direction? Yeah. Newton's third explains that almost everything that you thought about how things move is totally wrong. Put your pencils down. So I've done my long rant here, and I've tried to let you know almost everything about how you thought things accelerate. You're picking the total wrong force. What you're seeing is the force in the opposite direction. You're not actually realizing it's a different force pushing you or moving the object. Is that all right? Turn the page, or next page over. So how does Newton's third law help explain why it's difficult to walk or drive on ice? No, and when we talk about ice, let's imagine perfect ice with absolutely no friction. In real life, ice has a bit of friction. No friction means there is no pair force to bring you to a stop. Yeah. I did. Thank you for asking or remembering. This is where I forgot to unpause last time. Thanks for catching me. Okay. Forces come in pairs. You can't push on something without having it push back. And that also means, hopefully now I've convinced you, inanimate objects are applying forces all the time. You don't notice it, but yes, they are. They have to be. All of you right now are under the force of gravity. Everybody lift your feet off the ground. Right now, are you sinking into your chair, through your chair like quicksand? Are you flying off your chair like Superman? Right now, if I drew a free body diagram for you, the chair is pushing up on you with exactly what your mg is, whatever your mass in kilograms times 9.8 is. Put your feet on the ground. Now, your feet are taking a tiny bit of that gravitational force because the ground is pushing up to your feet a tiny bit. The chair isn't having to cover all of the mg now. The chair is only covering a little bit of the mg. Still most of it, probably about 90%, but not as much. Okay? If you pushed with both hands on the table, now some of the mg is being taken care of by the table pushing up through your hands. A great example, put your pencils down. Got to pause the video, make sure I don't forget to start it again. Mr. Dueck has a lame joke. It says a body at rest tends to play video games. Whatever. How does Newton's third help to explain why professional boxers need to wear boxing gloves? Pause the video again. You okay with that? I don't want to write a long paragraph. Oh, here's how we can write this. F of fist on face equals F of face on fist. If I was concerned about direction, I'd put a negative in there, but they're the same magnitude, so I'll leave the negative off. By the way, when boxers wear boxing gloves, does that make the mass of their hand heavier or lighter? See, it's counterintuitively, but boxing gloves, because F equals what? Since M just got bigger, with boxing gloves, they may look padded. You're actually hitting harder than with your bare hands. More force, has to be, because M just got bigger. Why do you lurch forward in a bus, turn the page, that suddenly slows? Or why do you lurch backwards when the bus suddenly picks up speed? What law applies here? Kedra, was that you? Oh, Abby, what? Okay, that'd be Newton's first. So you could say Newton's first, and I would give you full marks for that. If you can't remember which one is which, you could say the reason I lurch forwards is I want to keep going in a straight line at a steady speed until an unbalanced force acts on me. And the reason I lurch backwards was I was at rest and I want to remain at rest. I need an unbalanced force. And by the way, you didn't actually lurch backwards. You stayed at rest. It was the bus that lurched forwards underneath your feet, right? In this collision between, let's make this a big semi-truck and a little mini Austin to get the full contrast. Which vehicle experiences a bigger force in this collision? Since there's three choices, we're going to vote. How high you hold your hand up is how sure you are of your answer. I'm positive. I'm pretty sure, but I don't know why. I'm only guessing because Mr. Dueck is going to make fun of me if I don't vote. And I will. The only rule in my class is you have to at least make a hypothesis. I'd rather have you guess wrong than not guess at all. Okay? So which vehicle experiences the larger force? Who says, Dueck? A, the truck. The truck is going to experience the larger force. A, the truck. No one. Who says B? It's the car. It's going to get creamed. 1, 2. Ooh, a little controversy here. Who says they're both the same? 1, 2, 3, 4, 5, 6, 7, 9. 10. Convince me. You can either attack someone else's answer as that must be wrong, or you can defend your own answer as I must be right. Attack or defend. Convince me. By the way, don't assume that because only 2 people picked B, that must be the wrong answer. Trust me, as the year goes, I'll give you some really nasty head scratchers where most people will pick the wrong answer. Or maybe C is right because more people went with there. Convince me. Yeah. Truck has more inertia? Can you hold that thought? I'm going to come back to you. Can you remember what you just said? You just said it has more, and you said a word that begins with the letter M. Just remember that. I'm going to come back to you because unfortunately, C is the correct answer because forces come in. What law is that? So you could say Newton's third, or you could say forces come in pairs. The force on them is identical. But Matt, here's what you're confusing force with: damage. You were actually trying to answer, without realizing it, part B, the second part. Why is it that the car and driver are almost always worse off? F equals what? Truck, bigger mass, smaller acceleration. Car, smaller, experiences a way larger acceleration. You know what that means? In a car accident, it's not the force that does the damage, it's the acceleration that does the damage. You understand my argument? I don't want to write a paragraph. Oh, let's do this. We'll go F truck equals F car, because forces come in pairs. You okay with that, William? Which one has a bigger mass? F equals what? I'm going to go like this. Big M, little a, has to equal little m, mass of A. The car will have more acceleration, and that's why it experiences more damage. Matt and Matt, have I convinced you? Is that okay?
Yeah.
Okay. In fact, when the weather turns warmer, I have a t-shirt that I wear, and it says, it's not the fall that kills you, it's the VF minus VI over T. It's the acceleration. Okay. All of you have gone from 100 kilometers per hour to 0, just fine. You do it every time you're on the freeway doing 100 kilometers per hour, and then you go off the off-ramp, slow to 80, and then you go on the low heat and slow to 70, and you go to your subdivision, you slow to 50, and then you slowly pull into your driveway and your final speed is 0. But the time involved was so big that you hardly even noticed the acceleration. You took it for granted. Now that I've mentioned it to you, you might notice it next time, but really it doesn't interrupt your conversation or whatever you're doing. Okay? This would. What's your homework? Can you go to the very, 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 very last page? The question that says a man wants to test a rope. You can cross out number 4. And then if you go one page earlier to number 2 that says when you drop a tennis ball, it bounces back up off the ground. You can cross out that one. Now this seems like an awful lot of homework. It is. Next class, we're going to be watching about a half-hour Mythbusters video, and the rest of class will also be yours to work on this. I didn't give you the answers for a lot of these questions. We'll go over the answers near the end of next class, which I think for you folks is Tuesday. Okay? If you know you're going to be away Tuesday, then you have homework for the weekend. If not, you can probably get most of this done in class on Tuesday if you use the next 5 minutes to start the homework. If you look at number 1, by the way, Newton's laws, it says this. Nellie Newton weighs 300 newtons. That's the force of gravity on her. So what's the force on this scale right now? Got to be 300. What if we split it between 2 ropes? What's the force on each scale right now? 150? I'll let you try and see if you can kind of take it from there. That's the pattern we're getting at. Okay?